Hello everybody, welcome back to another video, and in this video we'll be looking at the Weierstrass substitution, which is a type of substitution that you can use for integrals where you have a rational function of sine and cosine functions, or any trig function to mention. So let's get started with deriving what the substitutions are. So what we need to do is we need to start off with, this is also called the half angle substitution, because we can say some variable t, or u you can say, but I'm just using t, is equal to tangent of x over 2. And this is the key idea of the Weierstrass substitution. So next what we can do is we can rearrange to solve for solve for dt in terms of dx, and then solve for sine and cosine, because we have a trig function, so we can do some things. So what we can do now, first of all, is take the arc tangent on both sides, because we know that taking the inverse tangent, so the inverse tangent of the tangent will cancel out. So taking the arc tangent on both sides, you'll just be left with the arc tan of t is going to be x over 2. Then we can multiply both sides by 2, and we can see that x is going to be 2 times the inverse tangent of t. So therefore, taking dx, so we now see that dx, derivative of inverse tangent, is 1 over 1 plus x squared, but in this case it's 2, because we still have a 2 there, and over 1 plus t squared. T is our variable now, because that's the input. So we have a variable, dt, of course, and now we can also solve for sine and cosine, and the reason we can do that is because we have t's tangent of x over 2. So what we can actually do is we can create a triangle, right angle triangle, and what we can see is that this angle here, which is x over 2 here, the tangent of that, which is the opposite of the adjacent, is t over 1, because t over 1 is just t. And therefore, this is the square root of 1 plus t squared. However, how do we get sine x? Sine x. Well, we can deliberately write this, sine x, as sine of 2 times x over 2, because by definition you'll just be left with the x. And what we can do here is we can actually use the double angle identity for sine, which is 2 sine theta cosine theta. So in this case we'll get 2 sine of x over 2 times cosine of x over 2, and that's all equal to sine x. And now we have everything in terms of x over 2. So guess what, here we can refer back to our right angle triangle and calculate what sine x will be. So let's calculate. So we have 2, we're going to have a 2 somewhere, and then we have sine of x over 2. So sine is opposite of hypotenuse. So therefore we're going to have a t over 1 plus the square root of 1 plus t squared, and then times cosine, which is adjacent over hypotenuse. So it's 1 over the square root of 1 plus t squared. And guess what? These are rationals, and we can multiply them numerator to numerator and denominator to denominator. And we can see that both of the denominators are the square root of 1 plus t squared. And therefore, multiplying it by itself, the squares roots will cancel. So this is actually just 2t over 1 plus t squared. So therefore, sine t, or sine x, in terms of t, is just going to be 2t over 1 plus t squared. And we'll see why this half angle substitution works so well. So here, now let's look at cosine. Cosine, we follow a similar process. We know that cosine, we can also use the double angle identity. So that's the same thing as cosine 2 times x over 2. And using the double angle identity for cosine, we can use any of the identities, but we know that the most basic one that comes from the summation formula for the cosine gives us cosine squared of theta, which is x over 2, minus sine squared of x over 2. Because if you use the sum rule, which is cos A cos B minus sine A sine B, you'll get exactly cosine squared theta minus sine squared theta. So in this case, our theta is x over 2. So this is what we have. And now we can evaluate these, because we know that the cosine of x over 2 is going to be 1 over 1 plus t squared, and squaring that entirely is going to leave you with 1 squared over the square root of 1 plus t squared, and then that is going to be squared as well. And then subtracting sine squared, which is sine, so sine is opposite of hypotenuse, so that's t squared over the square root, the square root of 1 plus t squared and squared. And very nicely we'll see that this squared and this square will cancel on both things, and therefore we'll be left with the same denominator, and we combine like terms, or combine the numerators, and we get 1 minus t squared over 1 plus t squared. And this is why the half angle substitution works so well, because we have the same denominator on everything. On our dx, our sine, and our cosine, we all have the denominator is 1 plus t squared. So we can see that here, therefore, cosine x is equal to 1 minus t squared over 1 plus t squared. So let's look at one quick example using this Weierstrass substitution. So we have the integral now, the indefinite integral of 1 over 2 plus cosine x. So this on its own is a bit tricky. Let's see, if you were to try to do this without using a Weierstrass substitution, it would be a bit tricky because we don't have any identities for this. So what we can actually do is we can replace our dx and our cosine with our Weierstrass substitutions. So what we can do is we'll take this to the t world, and this is going to be equal to the integral of 1 over 2 plus, and what is cosine x? Well, that is 1 minus t squared over 1 plus t squared. So 1 minus t squared over 1 plus t squared, and our dx is 2 over 1 plus t squared dt. So 2 over 1 plus t squared dt. So what we can do to make this a bit nice, well, first of all, we can see that this, oh wait, no, they can't. So what we can do is we can multiply by 1 plus t squared, and we'll see that we get this and this will cancel, so we'll get 2. So let's actually just take that out of the integral over, and we'll have the 2 times 1 plus t squared. So we have 1 over 2 times 1 plus t squared, and then this 1 minus t squared and 1 plus t squared will cancel because you're multiplying on the denominator as well to get an equivalent fraction. So to clear the complex fraction, so we have plus 1 minus t squared, and our dt is still there. So what we can see now is that we can actually begin to simplify a lot of things. So what we see here is that we have 2 times the integral now of 1 over. We can distribute this 2. We get 2 plus 2t squared plus 1 minus t squared, all on the denominator dt. That's equal to 2 times the integral of 1 over. And then we can see 2 plus 1 is 3. 2t squared minus t squared is just t squared. So we have 3 plus t squared dt. And guess what? We have a integral in the form of 1 over a squared plus x squared. And if you saw my previous video, we know that we created a general formula for that. And let's just make a note here. We know that the integral of 1 over a squared plus x squared dx is going to be 1 over a times the inverse tangent of x over a. So what we need to do is we need to figure out what our a is here. We have this in the form of a squared plus x squared. So therefore, our a must be the square root of whatever this constant is here. So our a must be the square root of 3. So now what we can do is we can actually just plug this into our formula, which now this comes to 2, and then 2 over root 3, because it's times 1 over a, so 2 times 1 over root 3, just 2 over root 3. And then we have the inverse tangent of x over a, but in this case it's t over a. So what we'll actually do is we still have a t there. So we have t, let's just write it as t times 1 over a. So t times 1 over a is 1 over root 3. And we can see that our t in our original substitution is the inverse tangent, or sorry, t is the tangent of x over 2. So plugging that back in here, we get 2 over root 3 times the inverse tangent of the tangent of x over 2 over root 3. And this is all in the fraction, and here we can put a plus c because we are done. And this is the power of the Weierstrass substitution. So this is it for today's video, and thank you for watching.